Okay, quiet. So you have r equals 1 minus 3 cos theta. So we've done this quite a bit now. So when you have a limicon set up this way where you have a plus b sine theta, a plus b cos theta, and the a is a value that's just by itself. The b is the number that's next to the trig function. And you take the absolute values of each of those. The sum of those absolute values of those constants would be the length of the outer loop. The difference, the positive difference, would be the length of the inner loop. And of course, if it's negative, then it's going to the left. If it's positive, it's going to the right. This for cosine. For sine, if it's positive, going up, negative is going down. So that should be pretty easy to graph. But if you want to be somewhat more accurate, you may want to try like pi over 6, pi over 4, pi over 3, stuff like that. Just see what happens. Of course, you could put in a Desmos or graphic calculator. But if you want like the curves to have kind of the right curvature a little bit, it's kind of good to plot points. And I'm not going to ask you guys to do it on our test, just so you know. And the test is not this week. It's not until after Thanksgiving. So I moved the test. I think I may have said that. I don't know if I said that. Actually, no, I did not say that because actually what happened was Thursday. Oh, Ethan, do you have a slip? Ethan, you have to get a slip. Oh, good. Thanks. Appreciate it. Thanks. Okay. So anyway, actually Thursday afternoon, I went up like just updating a lot of things to Schoology and preparing a lot of things. Actually, I even ran the test and took the test itself. And I made sure it's better this time because the last time wasn't great. And I still have some tests to pass back to you guys as well. Not everyone's got the test back, so I haven't passed back. Anyhow, I also have all the review stuff ready. So if you guys want the review stuff before we leave for Thanksgiving, you could do that. The test will be the Tuesday we're back from Thanksgiving break. So we'll have a review day on Monday. And I will have to spend a lot of time today, tomorrow, and Thursday covering all the stuff. My hope is Thursday we finish everything. No new material after Thursday for the rest of 2024. Come back, review for the test, review for finals. So we're getting close to the end, guys. Yeah.
Like you said, we are or not gonna have to draw.
No, you don't have to. No. Yeah, there'll be other. I'll share that later in the week. What questions I'll ask, but yeah, and then also Schoology all set up all the homeworks. Everything's. I just got to just put the video links in. So I really spent a good 2 hours Thursday afternoon just trying to get things all set up so I don't have to worry about it. So Schoology just have a lot of good stuff there. All the filled out notes are there too. So you got that as well. All right. So anyway, when you draw this, we draw counterclockwise, right? From 0 to 2 pi. That's how we do the unit circle, drawn counterclockwise. If you actually were to follow it on graphing calculator, it would look like this. Mode, switch to pole. Sorry. And let's do this. 1 minus 3 cos theta. Yeah, see how it goes counterclockwise, the rotation. I know it's kind of hard to tell because it went pretty fast, but that's what it does. Yes, correct. Yes. Determine the starting point. Yeah, just plug in 0. That's easy, not hard. For theta. Yeah, exactly. Well, actually, no. Find the zeros when R0. This is just plugging in theta equals 0. That's all. Part A. The find the zeros is deliberately saying R equals 0.
Oh,
that's just where it touches the pole. That's a different thing. I just plug in 0 for theta. That's that you can think of like that y-intercept. You want to think of like that. For D, symmetry. Now I will give you guys a formula sheet. The formula sheet's already in Schoology as well, so you know exactly what to expect. The formula sheet will look like this. Just so you're not worried. I will give you the sum of difference formulas because we did have to use that for the verifying the symmetry. And a test for symmetry, I'm not expecting to memorize that. So all the different ways to memorize to do it, I'll give it to you guys. So don't worry about it. So it's all set. And it's already up in Schoology. I also have sheets of paper if you guys want to hold on to it. And you'll get that for the test. David, go ahead.
Is it I minus theta? Like when you're looking for symmetries,
it depends on what type.
Because isn't it 2 times whatever?
Yeah, but it is pi minus theta. Yes, exactly. For theta equals 0, theta equals pi over 2. At the answer key?
Yeah, for D.
No, I'm not doing that. I'm doing r common negative theta for symmetry.
Okay.
Yeah. And
you can just
well, first off, here's what you have to do. When you test the symmetry, I'm not going to tell you which symmetry to look for because you should just look at your graph, right? Or if I give you a graph, right? And by the way, it will be graphic calculator allowed. So again, it's better test. Okay, graphic calculator allowed. So anyway, you can see it's vector about this horizontal axis. So you got to use that kind of test. So that's why I replace R with R and that theta is negative theta. It comes out the same. So symmetry is verified as a result. That I'll definitely ask. I'll definitely ask you to verify symmetry.
I thought if we're gonna make theta negative, we also had to not R.
No. For theta equals 0, you don't. To be spoken about the horizontal axis, you don't do that. That's with vertically do that. That's why I'm giving the formula sheet because it's hard to keep track of it all. So that's what I'm giving to you guys. Everyone gets it. For E, now this is where you gotta find zeros. Replace R with 0 and you just solve it. And that's you guys have done this before. And of course that's clearly a calculator question because you can't do inverse cosine of 1/3 from the unit circle. But it's not hard. It'll just tell you it's 1.231. But remember, cosine's positive in the fourth quadrant as well. You have to keep that in mind. So you have to find the equivalent angle in the fourth quadrant. That's your reference angle. So remember, a full circle is 6.28 or 2 pi. Take 1.231 away from that, you get pi from the 5 theta. So, and remember, we always state the polar coordinates as r first, theta second, r first, theta second. So because you're finding the zeros, you're at the pole, r is 0, right? You want to say that. So questions on those first 5 parts? Yeah, definitely D and E I'm going to ask for sure. I'll give you the graph. I'll give you the equation. So you don't have to make the graph. Don't worry about that. But I'm going to ask something like D and E for sure. And then probably F is a good one too. That's now this we have to be a little mindful about. This is a little tricky. So when theta equals 0, think about theta equals 0 is like this, right? The horizontal axis. But what other angle will we use to be on this horizontal? Besides theta being 0, we also use theta equals pi. So you got to plug in pi as well. When theta equals pi over 2, you got to investigate pi over 2, of course, and what else do you investigate? 3 pi over 2, 100%.
You put in 2 pi.
Yes, you do, because you are being asked to do it including 2 pi. So yes, we have to do that. Yeah. And when you do it, you just and that's easy. It's not hard. Just plug and chug. You have a calculator anyway, so it's not a big deal. But that's what you have to do. So you're gonna have to give me 5 answers, actually. Hope that makes sense. And then finally for G, and these answers are posted at School G as well, just so you know. I do have to make the answer keys for the rest of the homeworks, parts 3 and 4. But the homework for tonight is where the answers are up in School G, just so you know. For G, yeah, this is a good one. Like, what would produce the inner loop? So that's yeah. Well, here's the thing. You have to understand how the inner loop's being created, right? So why is it from 0 to 1.231? And I don't want you kind of playing around with it. It's really kind of ties back to what we did in part E. Because when you come back to the loop, you're going back to the pole, right? And the pole is when r equals 0. So you have to, it's really more understanding how it's being graphed. I think that's what you have to consider when you're doing part G, part 1. Remember what we said is that it starts at -2, 0. And it's going counterclockwise, right? So it gets back to the pole at 1.231.
1.231 is like that.
Correct, yeah. And then it does, so that's the lower half of the loop. There we go. That's just the lower half. Then all of a sudden it's doing some other stuff, right? After 1.231, let me switch colors, help you guys understand. So now we're doing, not the inner loop, but we're doing the outer loop, right? And when do we start doing the inner loop again? When we're back at 5.052 exactly. Does that make sense? How you have to think of it? So you really have to understand the process of which is graphed, but you get the graphing calculator to help you. David, go ahead.
So it's always gonna start in like the middle, like the inner.
Correct. 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 Right. So that's why it's going to be 2 separate intervals where the inner loop's done. It's not a continuous interval, right? There's 2 separate intervals. So you have to keep that in mind. But these notes are very detailed, so this should be a good guide. And then lastly, produce the portions as to the right. So the portions as to the right, I'll do that in, we'll say dark green. That's this here. So if you think about it, it starts at 1.231, but then goes to pi over 2 because it's hitting that axis. And then when it comes back around, it's at 3 pi over 2 and comes back around and goes up to 5.052. So it's the other portion. So it's really more just understanding the process of how this is graphed. So if I were to kind of color code this, so this part would be this part right here. And then this part, which I'll do in pink, will be this part here when it comes back. Hope that makes sense. So those questions I could ask too. David, go ahead.
This like doesn't really matter now.
Mm-hmm.
If you ask to the right of the line, they did pi over 2.
Mhm.
So you want us to say like greater than or greater than or equal to?
Oh, let's keep it equal to. Yeah, I mean, you don't have to. Well, it's always gonna be greater than equal to. It's or less than equal to. It's not gonna have the. It's not like the increasing decreasing stuff we did in the first unit where there was a bit of ambiguity. Don't worry about that. Good question. Okay, so we couldn't do number 2 because we haven't done rose petal, so we're gonna do that today. That'll be kind of fun. So any questions on this? We're good. All right, good. I'm glad homework didn't take too long. All right, so let's go back to the notes. And let's pick up where we left off. I think we finished cardioids last time. I didn't quite do all of it, but I think we did enough to make sense of it. Yeah, let me just show you the filled out notes, just so you know what we got. Okay, so remember we had this, and this is when the A and B values are the same. Like, you know, 1 or the absolute value of A and B are the same. So you don't get that inner loop, just because of the nature of the way the equation is written. We do get these dimples that's happening. It kind of forms a heart. And the whole positive negative thing still applies. The sine cosine thing still applies. Sine is vertical, cosine is horizontal. Positives up or right, negatives down or left. If you want to you know, change the range, you can to see what's being graphed. If you want to find the zeros, just plug in 0 for R. That's not hard to do. Define where it crosses theta equals 0, theta equals pi over 2 is all right there. I know we didn't do this, right? We didn't do these parts. Is that correct? Yeah, but I'm gonna kind of skip over it for now, because you do have access to these notes. But we'll do this for another problem. This whole process. I don't want to take too long doing this. What range of values produces the part that's to the right? So you guys already did it on the homework, but remember you have to look at where the zeros happen, which was at where was it again? It's 0 and 2 pi. And you have to also look at where you have to consider pi over 2. So that hopefully that makes sense. Why we get those portions the way we do. 0 pi over 2 is the upper half. 3 pi over 2 pi is the lower half. So whatever. The symmetry is the part I cared more about. To verify that algebraically. By the looks of the graph, it's pretty clear. We're looking at 2 minus 2 cos theta, it's horizontal. So theta equals 0 is a symmetry we want. So we have to use that rule, which is replacing R with R and theta with negative theta. There's another rule you could use as well, and that's going to be replacing R with negative R and theta with pi minus theta. But in all likelihood, we didn't have to do that because cosine's an even function. So that was not necessary. And we saw they're the same. So I know I kind of glossed over that. I know we didn't do parts 1 through 4, but don't worry, we'll do that kind of process for another type of graph just so you can get more practice. And you did that in the homework anyway. Now, remember what I said? Generally speaking, R equals A plus B cos theta, or A plus B sine theta. And if you take absolute A and B, remember they're equal to each other for the cardioid. It was the other way around where it was A is less than B for the limicon. But what if A is bigger than B? Okay, now that's the last scenario we have to look at. And that's going to be what we call dimple limicons or convex limicons. I'll give you the diagrams right now in the interest of time. So go ahead and jot those down first. And let me turn off the lights so you guys can see a little better. I was right at the sales score. I was off by 10. And we could talk Niners later today. I think we should fire the coach. Maybe we should all like wear Fire Shanahan shirts and make sure the GM's daughter, who's a senior here, sees it. We're 1 degree separation, just from the general manager. We're 1 degree separation. So yeah, Leo Lynch, yeah. Anyhow, a little frustrated. So yeah, so if you see here, still the same thing. The whole A-B thing. So in this case, A is bigger than B, or sorry, absolute A is bigger than B, absolute B. Look when we add these two. 7. Notice how that's the distance from the pole to the end of the outer part of it, if you want to call it that. And notice how this is 1, which is the difference between these two. And notice it's going to the right because of cosine, and it's positive. Here, notice it's going down, negative, right? The sign and it's negative, so it's going down. And that's the difference between hold on a sec here. That's hard to tell. But the sum of these two is 7, right? If you take absolute values, yeah, it goes down to 7 down here. And the difference of these absolute values is 3, so it goes 3 right here. So this is convex, clearly. That's dimpled. I mean, it's kind of hard to tell, but if you follow these rules here, it's kind of a funny rule. If it's between 1 and 2, and don't worry, I'm not going to ask you to graph these by hand. So don't worry. So like, oh my God, I have to memorize this. No, don't worry about that. You don't have to memorize it because you can have a graph calculator anyway, right? So it's all good. But just so you know how to differentiate between these two types of graphs. If the absolute A over B is between 1 and 2, that will result in a dimple limicon. If it's greater than 2 or equal to 2, then it's convex. Remember, convex means if you were to pick 2 points, remember, 2 points on a curve, sorry, on a shape, and the line stays within the shape, that's called a convex polygon. In case you guys got that from 2 years ago. Yeah. Anyway, Sean, go ahead.
So the distinction between like a dimple limicon
Mhm.
and arguably is that the dimple doesn't happen at the pole.
Correct. Yep. Yeah, exactly. Because dimple did happen at the pole. Yeah, that's good. Yeah, actually think about it, right? Because if these were identical,
Yeah.
then the difference would be
Yeah.
0, right? Then you wouldn't have that difference there. Then that difference would vanish, and they would be touching the pole. And you still get this part right here, as we've seen already. Yeah. So hopefully that makes sense. Mhm. When the absolute value of A over B is greater than or equal to 2, as the notes indicates. Oh, sorry. Oh, yes, yeah. That's going back to geometry. Yeah, if you were to pick 2 random points on a convex polygon or shape, whatever, and the line stays entirely inside.
Oh, okay.
Like where this would not be the case here, right? But if I did this, see how a portion of that is outside it? That's called concave.
Yeah.
Because it caved in.
Okay.
Does that make sense?
Yes.
Yeah, for those who are taking physics, actually, I'm not sure if you guys ever covered this on lenses, like convex, concave, mirrors, lenses, but anyway, I don't know if that's covered in physics anymore. Okay, so that's all that's happening there. Okay, next up, something called a lemniscate. It's kind of a funny name. So let's go ahead and get our graphic calculators. Let's graph this and just see if we can generate this graph. So I'm going to plot the first one. Yeah, it's kind of crazy. Actually, I'm gonna go to Desmos, because Desmos is better. So R raised to the second power equals 9 cos 2 theta. Oh, I gotta switch that up. Hold on. What? Okay, that's lame. Hold on. There we go. He doesn't like that either. Hold on. Ah, there we go. 9 goes to theta. All right. I don't think it really matters. Yeah, looks like it doesn't matter where you do plus or minus. So anyhow, okay, so you get that. And now let's investigate that graph a bit more. So these kind of look like a figure 8 in a way, or infinity symbol, or barbells. I don't know if you want to call it that. But you see how it goes out to 3, right? As a radius on each side of theta equals 0. So, I mean, if you were to plot the points, you would get that anyway. Because remember, the highest that cosine ever could be is 1, and lowest could ever be is -1. But yeah, that's what's happening there. What if I switch that to a 16? So see, it gets a little bigger, gets out to 4. So hopefully that makes sense. If you did a graphing calculator, you probably want that window as they indicate there. So describe it. Of course, it's horizontal. So what's the symmetry here? Theta equals what? 0. So we'll have to use that test.
Is there any way to like determine any other points other than those two? Other than just plugging in?
You can plug. You have to plug in points.
But you just
For
figure it out.
yeah, exactly. But that's why I'm not going to concern ourselves with that. That's why I'm going to give you guys a graph calculator.
Is there not also symmetry at theta equals pi over 2?
Actually, there is. Yes, good observation. Yes, there is. Yes, 100%. And actually, also, there's symmetry about the pole, theta equals 0, which we haven't really talked about yet. So there's 3 types of symmetry. There's also a rotation symmetry, which I haven't talked about yet, but we will get there today. That's if you rotate the graph 180 degrees, goes back to the same configuration. Anyhow, the length of center of graph to pull to one end. So A, that's what A does. Sorry, they're asking what A does. So in general terms, you think of this as square term or a square coefficient. So that's times that square, that's 3 squared, that's 4. So that gives you the length of the graph of the pole to one end of the lemniscate or the loop or whatever you want to call it. And what if you replace the cosine with sine? Now it gets a little funny if you do that. It gets a little funny. If you replace the cosine with sine, yeah, it does that. Why it does that? I mean, I think really just have to plot points. I'm not going to really kind of get too deep with that today. But if you were to plot points, it would look like that. Okay, that's how to loop. That's how it goes. And this will be a good tie into the rose petal. We're going to graph rose petals, rose curves later today. But just know it does that. And what values of R do you get when you plug in theta equals pi over 4? Well, I guess that's why it does that, because if you're doing 2 theta, right? What's 2 times pi over 4? Pi over 2. And remember, if you want to get that the length of the outer loop, or sorry, not the outer loop, there's only one loop. Let me turn off the inner one or the second one. Okay. So think about it, right? What's the largest value sine can ever hold? Any sine function. 1, right? The answer is 1. But then if you have root 16, right? So basically you're doing that to the 4. So you want to get this R value 4, right? But how will this become 1? It's 2 theta. The theta has to be what? The maximum sine value half is what angle? That's pi over 2, right? Or 90 degrees. But how do you make that pi over 2? Theta has to be pi over 4. Because 2 times pi over 4 gets you pi over 2. So that actually does explain why we see that. So it is the nature of the equation. But again, you'll have a graphing calculator at your disposal when you do these problems on a test. Yeah, so you plug in pi over 4, that's what happens. So those are the that's the length of the center of the graph at the pole to one end, if you want to think of it like that. Yeah, what's up? I'm sorry, what say that again? Lemniscate. Yeah, it's gonna be 2 theta. Yeah, I mean, we will see what happens when we change, because we're gonna change the coefficient of theta on rose curves For now, we're just looking at 2. Yeah, of course, no problem. Yeah, so again, if you're plugging pi over 4, r squared equals 9, so r equals plus minus 3. So you have 3 comma pi over 4 or negative 3 comma pi over 4. Because r is negative, it's going to rotate 180 degrees down to 5 pi over 4. So remember, you have this
What does it say when it says going up F FR?
where going up
Going up, right?
from left to right.
Oh.
Yeah, let's see it from. I've never seen it right like that before. That's weird. From left to right. Yeah, oriented at 45-degree angle along theta equals pi over 4, going up from left to right. Okay, now if we look at F, the symmetry is going to be kind of interesting, right? So if you look at the one with sine, it's not symmetric about theta equals 0. It's not symmetric about theta equals pi over 2. But does it have a 180-degree rotation symmetry? It does. Because what if I took this third and rotate 180 degrees around the pole? So the pole's a pivot point. If it rotates 180, you get back to the same configuration, right? The orientation. When that happens, we say it has pole symmetry. For pole symmetry, we haven't talked about yet. It's right here. You use one of these 2 things for pole symmetry. I'll give that to you. Don't worry about it. You don't have to memorize that. So you should replace r with negative r and theta with theta. Stay the same, cool. Or keep r as is. Replace theta with theta plus pi. And when you replace theta with theta plus pi, you will have to do a sum or difference formula, or actually a sum formula. So it's kind of a pain in the ass, but you know, you do if you have to. But I think it's easier to use the first type of test, the negative r theta, because you're squaring r. So guess what? If you square negative r, what do? It's still r squared. And you keep theta the same, so it's the same thing. You've proven the symmetry when you do that. And if you try the other test of symmetry, it just won't work. But why test the other ones if you have the graph? Just look at the graph, say, oh, it has to be symmetric about the pole, duh, look at it, and use that proper symmetry. I'm not going to ask you guys, you should not do this, by the way. If you do this, I'm going to stop. I'll try to help you if I see you do this on a test. You're not going to have to test all 3 of these. That's crazy. I'm not going to ask you to do that, right? If I made the test non-calculator, then yeah, you probably would have to. But I'm not going to do that because I'm not going to do that. I'm not going to torture you guys like that again. I promise. So that was not good. So yeah, I'll give you a calculator as you could see, or just give you the graph itself, right? So hopefully that seems pretty obvious what we have to do for testing the symmetry. Again, that's another test of symmetry, is testing around the pole. So now we have 3 types: theta equals 0, theta equals pi over 2, and theta equals, or sorry, and then the pole symmetry, which is a rotation symmetry.
And it's only for these ones.
Right. Yes, it's not a line symmetry. It's a rotate. Or rose curves. We could see that also. We're gonna get to rose curves in a moment. Yeah, that won't apply to limicons because they don't have that kind of symmetry, and it won't apply to the like cardioids or any kind of variation of that. So, okay. Questions? Before I move forward. Yeah, go ahead. Yeah. Oh, so well, first of all, do you see why it's symmetric about the pole visually? Do you see that? Okay, great. Because you rotate 180, get back to the same configuration. Then I'm just telling you that if you do these 2 tests, one of those 2 tests will work for you. That will prove it. If you want to, actually, maybe you're asking a different question. Maybe you're asking a deeper question, like why is that? Why does that work? Is that what that?
Okay, so if either of those give you the same.
I mean, I gather why this works. Because when r changes to negative r and keep theta the same, it rotates 180 degrees, right?
Yeah.
Or if you add pi, guess what? That's adding 100. Actually, great question. And sorry I glossed over that because we should talk. Yeah, let's talk about why does this work? Why does that make sense? It makes sense because we're deliberately or intentionally wanting 180-degree rotation. Add 180, keep r the same, or keep it the same and just switch to r, which we know, switch sine r, which we know is 180-degree rotation. We know that. So yeah, actually that does make sense. And the other one should make sense too, I suppose, right? Because if you're symmetric about theta equals 0, yeah, just keep r the same. Just switch your theta to the other side, right? That would guarantee that. Or if theta equals pi over 2, you want to switch both r and theta. The other ones are a little funny, but they work the way they do if you do pi minus theta. But I don't want to get into all that right now. Let's just keep moving. All right. Moving on to G. How would you change the equation of the function? So the graph is diagonally going from left to right instead of the other way around. So see right now, what's our symmetry? Wasn't pi over 4? The graph pi over 4. Right? It's going diagonally this way. But what if I want to go this way? What if I want to do that? How would I change things up in the equation? Yeah, so what we'd have to do is we have to add pi over 2. We have to do a 90 degree rotation. Why am I doing a 90 degree rotation? Because right now, this dot here is at pi 3 comma pi over 4. Now I now want it at 3 comma 3 pi over 4. How far is 3 pi over 4 away from pi over 4? Pi over 2. Or you can rotate the other way as well. You can rotate clockwise or counterclockwise, fully up to you. But when you do that rotation, we're going to see that happening. And we talked about, I think I'm going to the beginning of these notes. We kind of talked about rotations, I think. Yeah, we talked about that, right? If you do theta minus k, it rotates whatever k is, right? So yeah, I'm just applying that. That's all. So that should be pretty straightforward, hopefully. Okay. I know I'm being a little lazy here, but not writing this out. But you know what? I'm being efficient here too. Let's just think of that way. But I think I'm doing a good job narrating, so I'll give myself that credit. So anyway, so in conclusion, here are all the types of symmetry, and I'm giving this to you guys. It's good to write it down, though. It's good to write. When you write it down, hopefully you just know what to do, you remember what to do. But I'm going to give these to you. But as I just explained to David not too long ago, right? The pole seems pretty obvious now, right? 180 degree rotations, which are negative r or at pi. The polar axis seems pretty obvious too. Like keep r the same, but instead of theta this way, go theta the other way. Yeah, that's going to guarantee the horizontal symmetry. For the vertical symmetry, a little tricky, but if you switch the theta and switch to r, that should get you the left right, like with the vertical axis of theta power to be symmetric. These are kind of funny ones. I'm not going to really think too hard about these, but they work. You can use them. The r comma pi minus theta or the negative r comma pi minus theta for theta pi over 2 or theta equals 0 respectively. So I don't know. Those work, I guess. We could investigate that further if we wanted to, but we don't need to. Okay. Yes, yeah, go ahead.
So, like, on that's not a problem. Will we have to? We don't have to check for all 3 types of right?
No. You will be able to tell. Well, first of all, I mean, I'm not going to tell you which one to use, but you'll have a graph, and you should be able to tell from the graph. Like if I give you this graph, don't waste your time doing theta equals 0, theta equals pi over 2. Do the pole symmetry. If you do the other ones, you're going to be spinning your wheels. Don't do that. Okay. Rose curves. Okay, these are the fun ones. And this has a really cool pattern to them. Yep. So let's talk about this. So here's what's happening from observation standpoint. If you have an odd number of petals, sorry, let me take it back. If you have an odd number in front of theta, you have precisely that number of petals. Does that make sense? If you have an odd number in front of theta, like here we have 3 in front of theta, you have precisely that number of petals. And generally the form will go like this: r equals, so it's not the r squared thing, the square root, it's none of that business. It's really just r equals a cosine with something times theta. And you can have a coefficient in front of the trig function as well. So now if you have an even number in front of theta, the number of petals will be doubled. So if you have 2 theta, we have 4 petals. If you have 6 theta, you have 12 petals. If you have 10 theta, you have 20 petals, and so forth. But if I have 7 petals, then 7 petals. Sorry, 7 in front of theta, 7 petals. 5 in front of theta, 5 petals. So keep that in mind. I think that's a pretty easy observation. Like look at r equals 3 sine 4 theta. How many petals do I got there? 8. But look at 4 sine 5 theta. I have 5 petals. So I'll move down in a moment. Questions? About the oh, just if it's an odd number in front of theta, that's precisely the number of petals I have. So if I have 3 theta, I'll have 3 petals. If I have 5 theta, I'll have 5 petals. If it's odd. If it's even, I double them. I double that number to get the petals.
Okay.
If I have two, they have 4 petals. Fourth, they have 8 petals. So that's just an observation. Actually, correct. Correct. Right. Yeah, the number. Does that make sense? All right, cool. So I'll put this somewhere off to the side there. Whoa, what's going on? That's weird. Okay. Now, the orientation is a little funny though. Okay, if it's cosine, here's the deal with cosine. Cosine is always going to start on the polar axis. Because think about it, right? If theta equals 0, if theta equals 0, what's your output of the cosine? 1, right? And if you have a coefficient, great, multiply it by 1, done, right? So this one here, see how linked is 2 to the petal? Or see how linked here is 1? So hopefully the starting petal makes sense, right? The starting petal has to be there. After that, the rest of the petals are all not symmetric necessarily, but they're all split equally, right? You think about it, if you have 4 petals, first of all, how many degrees is a full rotation of a circle? Or in terms of radians, 2 pi. So you gotta just partition that 4 equal ways. So 0, 90, 180, 275, 360. Or 0 power 2 pi, 2 power 2, 2 pi. Likewise here, if you chop up 360 3 ways, what's 360 divided by 3? 120, great. 0, 120, 240, 60. Simple, right? Not that hard. Now the sign's a little funny though. The sign does not start at the polar axis for obvious reasons, because sine of 0 is 0. It's not terribly obvious, but what you need to do is ask yourself this question. What does they have to do to make that pi over 2? Right? Because then sine pi over 2, 1. So essentially set this equal to pi over 2 to solve for theta. If set this equal to pi over 2, what does theta equal? Pi over 10, right? Now, if you think about it, 360 divided by 5 is 72 degrees if you think about a pentagon, or 360 divided by, 2 pi divided by 5, of course, is 2 pi over 5, right? Well, pi over 2, I know is 5 pi over 10. What's 5 pi over 10 minus pi over 10, guys? 4 pi over 10, which reduces to 2 pi over 5. So essentially going 2 pi over 5 rotation-wise. So there's a rotation symmetry, of course, 100% is rotation symmetry. You have to rotate it that way. So you're chopping up 5 equal ways because you got 5 petals. But because we do this in radians, not degrees, so 2 pi divided by 5. So every 2 pi over 5 rotations is what I'm seeing for the petals. Starting at pi over 10, because that's what makes that pi over 2 on the inside. Hope that makes sense. Like the other one here, what makes that pi over 2 pi over 8? How many petals I got? 8, right? 365 over 8, 45 degrees, or do 2 pi over just pi over 4. So I can rotate by pi over 4 units, which is 45 degrees. So fun with that. Let's see. That'll be 3 pi over 8, 5 pi over 8, 7 pi over 8, 9 pi over 8, 1 pi over 8, 50 pi over 8, 50 pi over 8. Kind of crazy.
And it's not. That's right.
Mhm.
Holding for that last one, I don't know if it's like
Mhm. 7 pi over 8.
Earth 4 sine
Mhm.
5 theta.
Mhm.
Having some of them
Mhm.
like,
Have negative R. Yeah. That's just them being kind of cute about it. Honestly, you could just you didn't have to do -5. You could have done like 5 comma. If I had a 4 pi over 10, that could be 13 pi over 10. I could have done that.
Then it's 5 and the other one's 4.
Oh, yikes. Yikes. Oh, these are supposed to be, oh my gosh. Good catch, guys. Or did not see that. Thank you. Yes, that should be four. Yes, that's a typo. Thank you for pointing that. Wow, oh my gosh. Well, I didn't make these notes. So yeah, okay, well, I'll do better G period because it's narrating these. So yes, sorry, those should be fours. Yes, those should be fours. Should be four. Yeah. Yeah, A is the length of the pedal. Just so you know. So that's going off rose curves. No, just kidding. Right. There we go. Okay, I'm feeling good here. We're gonna get all this done. This is great. So it means that we'll do part 3 of the notes on Tuesday and part 4 on Thursday, and then we're done with new material for 2024. It's awesome. Now enjoy Thanksgiving break and start testing. All right, feeling good here. All right, how does the value of n determine number of leaves? I already explained that again. If n is odd, then you have n number of leaves. That's kind of a play on words. If you personified n leaves, get it? It's leaving. Okay, I'll stop. All right. Okay. Dumb dad joke. All right. Then the n number of leaves, right? As of now, not a verb. Okay. If n is even, then there's 2n leaves. Okay. Kind of a fun pun there you could do with that. How does sine versus cosine affect? I already explained that. Cosine is always one leaf on the polar axis. Axis symmetry, theta equals. Well, yeah. I mean, if you look at cosine, it's not going to always have. Well, let's come back a little bit here. Let's think about the symmetry really quickly. I'll come back to notes. This has symmetry about theta equals 0 and theta equals pi over 2 and pole symmetry. This does not have theta equals 0 symmetry. It doesn't have theta equals, sorry, it doesn't have theta equals pi over 2 symmetry. It has theta equals 0 symmetry for sure and rotation.
Right.
This has theta equals pi over 2 symmetry, but not theta equals 0 symmetry. This has actually both. Theta equals 0 and theta equals pi over 2. And all these have pole symmetry for sure. 100% they all have pole symmetry.
Just because it's cosine of sine.
Actually, wait one sec. I lied. No, it does not. The second one does not have pole symmetry. The first one does. The second one does not. The third one does. The fourth one does not. So it's the whole odd even thing with the coefficient of theta. Sorry, my apologies. Yeah. So we do have to consider the graph, right? Let's look at cos 2 theta. Clearly, this has all 3 levels of symmetry. So you got to test all 3 of them to prove it. And if you do test it, especially about the pole, you can replace R with negative R. It doesn't work for us, and theta with theta. But if you keep R as is and replace it with theta plus pi and use a sum formula, you will verify that symmetry. So the symmetry is confirmed there. The symmetry about the pole. So again, I'll give you these formulas. Don't worry about that. But you have to kind of, if I ask you, hey, prove the symmetry for me, prove this, symmetry about the pole or whatever, you're gonna have to use the proper symmetry test and then show that to me. So I lied. It wasn't not always symmetry about the pole. The even ones looked like they were when the coefficient of theta is even. Yeah. Okay. So I think that should about cover it for today. Quick question: how long did it take you guys to do the homework? That number 1 to 7 parts. How long did you say it took you guys? Do you feel like you'll be better at it now, or okay? So I'm gonna have to be mindful about the homework I'm assigning tonight. Then might be a little too long. Maybe I'll assign just 1 or 2 problems, and then the rest we do in class tomorrow. Homework. What I was thinking. Okay, don't get mad at me. I was thinking, let's see here. And I could totally adjust it, not a problem. Um, so definitely number two, right? And this is a rose petal. How many petals will this have, guys? Three. And what's the length of each rose curve? Two. Good. There we go. You guys will be great. So you'll sketch it in Desmos, do the sketch, symmetry, all that fun stuff, right? Just go through the motions there. Okay, I was thinking of signing all of handout B as well, but that's too much. That's way too much. So I think what I'll probably do is I'll probably do yeah, it's a little much. Okay. I'll remove numbers. I'll remove number three. That's too much. Um, but since you do have a calculator, um, you guys get a head start now. If you want, we got 10 minutes. So yeah, we'll do number two of handout A. So pages 3 and 4. And then numbers 1 and 2 of handout B, pages 5 and 6. I'll remove number 3. We'll do that as a class tomorrow. So we won't do 7 and 8. I'll remove that. Because the other handouts are pretty short. They won't take very long. So I'm confident we can get all this done. And the lesson for tomorrow is also really short too. Because now we got into page 18 of these notes. The next one's just 19 through 21. So we'll have plenty of time. So I'll chop off. Let me go to Schoology really fast. And let me update this really quickly here. Crap. Hold on. Yeah, so we're on homework number 26. There we go. Easy peasy. Okay, just update it. All right, we're all set.